All right, now we come to our second lesson on moving fluids. This one involves the pressure in a moving fluid and eventually getting to Bernoulli's principle. So again, we're going to start with a question. We want to figure out what things affect the pressure in a fluid. So the first one we're going to look at is how does the velocity affect the pressure? We already learned last lesson that the velocity itself is affected by the size of the tube or the diameter of the tube. And we came up with our continuity equation that says the area times the velocity at one point equals the area times the velocity at another point. So we know how to find the velocity of a fluid flowing in a tube. Now we got to figure out how to predict what pressure that fluid is going to be at inside that tube. Now, we had some ideas when we talked about static pressure where it's based on the pressure at some other point plus rho gh, where h is the depth that you're at. But we want to see if that holds true or if something's different when a fluid is moving. So first, let's see if the changing velocity affects anything about the pressure. So again, make a prediction. Here we have our tube is getting bigger, so we know the velocity is going to decrease as the water flows from left to right. So make a prediction what you think is going to happen to pressure, and then we will see. So again, the velocity is slowing down. We can see it goes down from 6.4 down to less than 1 meter per second. And if we look at the pressure, it seems like the pressure is increasing as the velocity of the fluid decreases. So we can kind of say, again, we don't know exactly how true it is, but it seems like as velocity decreases, pressure increases. And hopefully you also saw that when you did your lab in class. So let's test another case. Because we know we can have pipes that aren't just always moving horizontally. So what about a pipe that moves sideways but also moves up and down? So here we have a case where we set the tube radius to be constant, so we know the velocity is going to be constant everywhere. But now we want to figure out how does the height that the tube is at affect the pressure inside the tube. So again, think about your answer might be, make a prediction. Let's take a look. Again, the velocity looks like it's going constantly. Let's check it out. It seems to be 6.4 for all the different spots. And as we check out the pressure, in the beginning it's about 90, and it looks like down to the lower spot it's 110, in the middle it's about 105. So it seems like as the height of the tube gets lower and lower and lower, the pressure increases. So again, we're not sure exactly if it's linear or anything like that, but it seems to be as the, let's call it y, that's what your book probably calls it, as y decreases. Now y, let's just say like there's some, remember, you always got to measure heights based on something. So we could call this y. That could be like y2. And that would be like y1. So as y goes down, it seems like the pressure increases. And it's something you also should have seen when you're doing your lab experiment in class. So I'm not going to go through all the results of your lab experiment, but I'm going to try to use, again, some physics principles to theoretically create an equation that should match the results that we saw in class and match the results we just saw there. Now, I will tell you, when a pipe does change its height, because there's actually more than just two things changing, it does get a little more complicated. It's not as simple to write down as some of our other equations. So it gets a little bit weird, but we'll see when we start solving some problems that a lot of times we can make some assumptions that clean this equation up a little bit. So I'm going to start, though, by going back to last year and thinking about something as simple as like a ball sliding down a hill. I didn't say rolling. I'm not going to worry about rotational motion, but it says a ball rolling, but let's not worry about rotational stuff. So just like a ball sliding down a hill. And if we think about that and think about what energies the ball had, because no conservation of energy is true. If we think about the ball, the energies the ball had sliding down a hill, we know that it had some kinetic energy. It could have some potential energy. And there could be work being done. It could be pushed down the hill. So we'd say there could be kinetic energy. Let's actually separate this a little bit. And we might write kinetic energy plus potential energy. There's no spring potential here, so we don't have to worry about that. And that could be at 0.1, and that's going to be equal to, at some other point when it's farther than the hill, the kinetic energy at 0.2 plus the potential energy at 0.2. And if we threw some work in there, there could be some work done on it that changes the energy states of these things. And now if we wanted to figure out kinetics and potential energies, we have to kind of do some measurements. So let's call this Y1. Let's call this Y2 over here at the end. That means it's going to have some velocity at 0.1. It's going to have, we already wrote Y1, I'll write it again here. It's going to have some velocity at 0.2. It's going to have a height at 0.2. And because we're asking about pressure, I'm also going to kind of write as a variable a pressure at 0.1 and a pressure at 0.2. Because we want to see how they're related to each other. Now, if we just start with our conservation of energy equation here, the next thing we normally do is expand this. So if we expand this equation, we get something like that the kinetic energy plus the potential energy at 0.1 plus now work is force applied over a displacement plus the work being done is going to equal the kinetic energy at 0.2 plus the potential energy at 0.2. So that's nothing new to us. Now, what's going to change up a little bit is because we're dealing with a fluid, we're going to do a little trick. I'm going to divide this entire equation by volume. The entire thing I'm going to divide by volume. And then we're going to see something nice happens. You can already kind of see, well, if I divide mass by volume, I get density. So every mass term I have is going to turn into a density term. So that means this first one's going to become 1/2 density times velocity 1 squared plus density times GH. Or I used H here. I'll keep using H even though I said Y before. I believe some equation sheets and books a lot of times use Y. Well, we'll get back to the work in a second. And that's going to equal 1/2 times the density times the velocity at 0.2 squared plus the density times G times H at 0.2. So that's nice because when we deal with fluids, we like using densities rather than masses. So that helps us out a lot. Now, if we come back to our work term, if I look at work, let's come over here to the right. And I say, okay, force times displacement divided by volume. That's a little bit ugly. Can I clean it up at all? Well, if I look at some of the terms, so if my object is moving to the right, and I'm thinking, what's doing this work? So the pressure is going to sneak its way in here in a second because pressure is the actual thing doing the work. It's applying. That's how the force is being applied, is the pressure inside of these fluids. So if kind of pressure is doing the work, and it's being applied sideways, I can kind of think about this volume here as really a cylinder volume again, and it's called this volume. It's really an area times some displacement, or a delta x, or a delta d is kind of like the x direction piece of that. And if I plug in area times delta d in for the velocity or for the volume, I can see, well, these terms are going to cancel out, and my work per volume ends up equaling just F over A, which is pressure. Now I got to be a little bit careful because there's a delta D in there that we're canceling out. So this really becomes a delta pressure or difference in pressure over there. So now I can do, not really a trick, but one more little trick. I'm going to say, well, this is a delta. So I'm going to break it up into P1 minus P2. Just a difference because the deltas are differences. So that's a difference in pressure. And now if I bring this term to the other side, I have our final version that just says that 1/2 density times velocity squared at 0.1 plus density times G times, now I'm going to I'll keep it as H at 0.1 plus the pressure at 0.1 is equal to 1/2 the density times the velocity at 0.2 squared plus the density times G times H at 0.2 plus the pressure at 0.2. And this is what's known as Bernoulli's equation. And really it comes straight from just a conservation of energy. A simple conservation of energy equation where it's really conservation energy per volume where we divide it out and we get this nice relationship that says for any point along our flowing fluid, again, as long as it's, we can assume it's incompressible, and as long as it's like actually a full tube of fluid going through there, that these three terms, the 1/2 the density times the velocity squared, density times g times h, and the pressure, now remember, this is not the outside pressure, this is the pressure in the fluid, that those three terms added up have to be constant throughout our entire fluid. Now let's look back and see if it kind of matches up with our two experiments. So in the first experiment, we held the height constant, and we said what happens to the pressure as the velocity changes. Well, if the height is constant, this term and this term we don't have to worry about. As the velocity goes up, as this term increases, this term has to decrease because the sum of those two has to stay the same. So that matches up. The other one was we held the velocity constant, we changed the height. So that in that case, this term we don't have to worry about. And then if we look at, it's really saying that the density times g times h plus the pressure, that's got to remain constant. So if the height goes down, the pressure has to go up. And again, this is called Bernoulli's equation. Named after Daniel Bernoulli. And again, yes, it looks a little bit ugly. There's a lot of terms in there. It can be a little bit confusing. There's a lot of densities. There's a lot of variables that look the same. But we're going to see as we work through some problems, it's not going to be too difficult. And that's the last thing for fluids. So kind of to sum up, if we look at our equation sheet of where to find these things, there is our continuity equation we learned about. There is our Bernoulli's equation that we learned about. And really, we can answer almost any question about a moving fluid. Again, if you go to college with this stuff, there's going to be a lot more, it gets a lot more complicated if you kind of take in a lot of other factors. But for our simple cases, we can answer almost any question about a moving fluid simply by using those two equations together, where we use the continuity equation to get the velocity usually, and then we use Bernoulli's equation to get pressures or anything else that we're looking for.